The second part of the notes today starts off with a proof, and you're proving why the diagonals of a parallelogram bisect each other. And so this is just, it's good practice to go through and see why these things are true instead of just writing down that they're true randomly all the time. So we'll go through this proof together and I'll explain the steps for you. You're given that ABCD is a parallelogram, and you're given that AD is congruent to BC. So here are the two things that you're given. They put the parallel markings on the picture for you. Remember that these two little lines right here that go vertically are the symbol for parallel. So step number 2 says, because ABCD is a parallelogram, you know that side AD is parallel to side BC. The reason why that's true is because that's that is the definition of parallelogram. It's not one of the properties that we listed. If you flip back to the first page in your notes, the definition of parallelogram says both pairs of opposite sides are parallel. So they tell you right here that it's a parallelogram, and then the reason that this is true is because it's a parallelogram. Now that we know that these two sides are parallel, they're saying that angle DAE is congruent to angle BCE. So they're saying that you know that this angle right here is congruent to this angle right here. Picture if you traced the whole way across. You see how those two make the letter Z? They're inside the parallel lines, but they're on opposite sides of the transversal. The reason why those two angles are the same is because of the alternate interior angles theorem, so AIA. AIA says that if you have a parallel line and a parallel line, and if the two angles are on opposite sides of the transversal, then those angles are congruent to each other. We need to now mark that on the picture though. So I'm going to say that this angle is congruent to this angle. Step number 5 says something different. Step number 5 says, why is angle AED, so that's this angle in the middle, congruent to angle CEB? So why is this angle congruent to this angle? And the reason for that is because those two angles are vertical angles, and we know that vertical angles are always congruent to each other. And so if we stop right here, we forgot to mark, I forgot to mark this one on the picture. So I forgot to say that even though AD and BC were parallel, I'm going to put the markings on them to show that they're also congruent to each other. So you guys, when you get to step number 6, you should have all of that marked on the picture. Step number 6 says, why can I now say that this triangle over here on the left, triangle ADE, is congruent to triangle CBE, so this triangle that's over here on the right? So the reason why I can say that those two triangles are congruent to each other is because I know that this angle is the same as this angle. I know that this angle is the same as this angle. And then I know that the side that's not between them is the same as the side that's not between them, those two angles. So the reason for this is AAS, angle-angle-side congruence. And then because of angle-angle-side congruence, I can use that to prove what I was trying to prove, which is that this diagonal gets cut in half. So the reason why this is congruent to this, why AE is congruent to EC, is because of CPCTC. So this proves that this one is the same as this one. And then I could do one more step to prove that this one is the same as this one, and that would be CPCTC as well. So in a parallelogram, because of what parallelograms mean, the diagonals bisect each other, and this proof shows you that. The last two problems over here on the left have to use they have to do with the diagonals property. So on the front of your notes from today, one of the things that you wrote down said both diagonals bisect each other. And so if you look at examples 3 and example 4, they're having you practice that with the diagonals. So, and then a little bit with the sides too. So I guess we have to use both of them. So 2z plus 4 is a side, 3z minus 4 is a side. And so from the previous part on the notes, we said that both pairs of opposite sides are congruent. So we'll set them equal to each other when we solve. And then x plus 9 is this piece of the diagonal, and 4x plus 6 is this piece of the diagonal. And we said on the other side of the notes today that both diagonals bisect each other, so we'll also set those equal to each other to solve. So 3z minus 4 is equal to 2z plus 4. And I put lines through my z's so that you know that they're z's. So when I solve this, I'm going to minus the 2z from both sides. and I'll get z equals 8. And then I also need to solve for x. So when I solve for x, I'm going to use the fact that the diagonals bisect each other. So I'm going to set 4x minus 6 equal to x plus 9. It doesn't matter which one you put on which side. You'll get the same answer. So I get x equals 5. And then I didn't really leave myself room to do this, so I'll just do it in the middle, I guess. They also want me to figure out how long is it from Q to R. So Q to R is this side that's over here. So I'm going to plug in the answer that I got for Z, which is 8, in right here. So I'm going to do 3 times 8 minus 4, which is 24 minus 4, which is 20. So I'm going to get the length from Q to R is equal to 20. Do you notice how I leave the little segment notation off on QR? I'm actually doing that on purpose. Whenever you write 2 letters like this and you don't put the bar on top of it, that means that you're talking about the length for how long that segment is. Okay, so 4 is just another practice of the same thing. These are opposite sides, and we know opposite sides are congruent. This is half of the diagonal, and that's the other half of the diagonal, and we know that the diagonals cut each other in half in a parallelogram. So you guys, when I solve for 4, I'm going to do the same thing that I did up here. I'm probably just going to flip-flop the way I write these two. So 5z minus 16 is equal to 3z plus 8. And so I'll start by going through and solving for z. So I get 2z equals 24, so z equals 12. And then once I have z equals 12, the next thing that, let me just adjust the focus on this a little bit for you. Good. So the next thing I need to do is I need to figure out what w is equal to. So I'll set the 2 pieces of the diagonals equal to each other. So 4w plus 4 is equal to 2w plus 22. W is equal to 18. So this will let me figure out that w equals 9. And then once I have w equals 9, the last thing they want me to find is they want me to figure out how long is it from E to H. So when I plug in my answer, I'm looking over here because they want me to figure out how long is it from here to here. So I'm going to take the 12 that I got for Z and I'll plug it in right here. So 5 times 12 minus 16 is 60 minus 16, and so I get 44. So the last answer to the question that they wanted me to find was how long is it from E to H, and so I get from E to H is 44. Basically, with parallelograms and the kinds of questions that we practiced in the notes today, you're deciding whether you're adding things up to equal 180 or whether you're setting things equal to each other, and so that gives you a little bit of practice with each of those things. This last question on the notes right here is asking you to put an X in the box of the shape that always has the given property. So they want to know what are the things that are true about parallelograms. So when we're looking down this list, there's a couple of things that are sometimes true about parallelograms, but we're only going to put an X if it's always true. So the first box says all sides are congruent. That's not true about parallelograms. There are shapes like squares and rhombuses where we will put an X for this one, but parallelograms don't always have all sides congruent. Parallelograms do have both pairs of opposite sides congruent, so this is always true about parallelograms. This one says both pairs of opposite sides are parallel. This is also always true about parallelograms. When this one says exactly one pair of opposite sides are parallel, that's going to be true about trapezoids, and we haven't learned about trapezoids yet, so you don't have to worry about marking that one. All of the angles in a parallelogram are not congruent to each other, but there is something with the angles. It's just not listed in this list. We know that opposite angles are congruent to each other. This one says exactly one pair of opposite angles are congruent to each other, and that's not true because we know that both pairs of opposite angles are congruent to each other. This one says the diagonals are perpendicular, and that's not true about parallelograms. It says the diagonals are congruent, and that's not true about parallelograms. But in parallelograms, the diagonals do bisect each other, so we know that that's true. Down here in the bottom, there's two other things about parallelograms that I would like you to write down. Let's see. Looking back at the front of the notes, we got both pairs of opposite sides are parallel, so we got this one. We got both pairs of opposite sides are congruent, so we got that one. This one wasn't written down, so what I'd like you to do is I want you to add this one in. Both pairs of opposite angles are congruent. So that one's true. We got that the diagonals bisect each other, and so there was just one other one on the front. All four pairs of same side interior angles are supplementary. So let's write that one down too. All four pairs of same side interior angles are supplementary. These are, so you guys, these are the 5 things, 1, 2, 3, 4, 5, that you need to remember about parallelograms all the time. Knowing these will help you moving forward with all of the different kinds of quadrilaterals that we'll be practicing during the rest of this unit. So just one more reminder, make sure that you do both of these online tonight. So 24.1 and 24.2.